Okay, let's talk about image compression. Why do we need to compress the images? How do we compress them? And what are the consequences of image compression? To understand compression, we need to understand how the computer displays the image. It uses pixel values. These are a matrix of numbers that match the grayscale values in the image. Let's use a picture to explain this. Do you see Abraham Lincoln? Hopefully you do. This is what the computer sees. It just sees different values from white to gray to black, and it uses a matrix of numbers to create so many black pixels or so many white pixels or so many gray pixels so that each square, each block in that matrix has the right value to create the image that you see. So here's the why. Image compression is in constant demand as the only practical way to deal with ever-growing imaging data volume. More studies than ever before are being done. Each study has more images than ever before. The data sets are growing faster than the network can handle it. So there's two main types of compression. Lossless compression does not change the original image, but achieves a rather modest 2 to 4 compression factors. Lossy compression can typically reduce data volume by 10 to 20 times, but you need to be aware of the irreversible artifacts that it introduces into the images. So how does it work? Sure, I know how image compression works, you say. It removes image pixels to make the image smaller. Actually, compression is the art of rewriting the original information in the most condensed form. In fact, I bet you've been practicing the theory of image compression without even realizing it. When you remove letters to compress words in a sentence, you are performing the same function as image compression. You might turn "you know that you are what you eat" into "you know that you are what you eat." You simply pick the most frequently used words such as you and are and replace them with the shortest possible code words. Presto! You just built a simple compression dictionary. Your original "you" is now represented by the code word the letter "u." Your original "are" are now represented by the letter "r." That's a compression dictionary. So image compression doesn't remove pixels to make the image smaller. It simply rewrites the pixels in the shortest form possible. You've been practicing lossless compression in your text messages. It's obvious that if you keep replacing the most frequent patterns with the shortest possible code words, you will shorten the data in the most efficient way. This is precisely what most lossless compression techniques do. These algorithms may rely on more advanced approaches to achieve the optimal encoding, but the essence of compression is the same. Replacing the most redundant patterns with the shortest code words does the job. Lossless compression is reversible. Compression attempts to encode the original data in the most compact form. This encoding is reversible. The original data can be fully recovered from its compressed representation by using the values from the compression dictionary. Therefore, reversible compression is also known as lossless. Compression is quantified by a compression ratio. So RC or RComp is the original data size divided by the compressed data size. Lossless compression can do a great job in many cases, with a typical RComp ranging from 2 to 4. But lossless may not be effective when one runs into mega and gigabits of data. So we need to go lossy. Medical images are really big files. One image pixel takes roughly the same memory as one letter. Now imagine that you have to store a CT image exam that's 500 images, for instance, along with some textual data of, say, 10,000 letters. Patient demographics, history, the report. 10,000 letters may seem like a lot, but a standard 512 by 512 CT image has 262,144 pixels, which is already 26 times the size of the accompanying text. Now, if you multiply 262,144 by 500 images, you should get the full picture. Medical images take a lot more space than medical text does. Big files. So we need to target the images, and we need to compress them very efficiently. Just as we discussed earlier, images are a sequence of pixels. One can read them line by line, starting from the top left, and they may have values like this: 1,000, 1,000, 1,103, 102, 1,005, 1576, 1623, 1627, 1620. We can definitely apply lossless compression to it. For instance, replacing values of 1,000 with the shorter code word X, that string becomes All right, so here's the original string here, and now by applying x, we have 3x, which represents this 3,000s, and then 103, 102, right? Same string of numbers matches. So this looks good, but for most images, this would only yield an RComp around 2. Good enough to save on disk storage, but hardly enough to send that CD case to a smartphone in real time over a jammed network. Can we compress it any stronger? Yes, lossy compression is the answer. If we adopt the ideal of irreversible lossy compression, achieving our comp through slight alterations in the original pixel values, indeed, the difference between pixel values of 1000 and 1003 may not have any diagnostic meaning. You may not even be able to perceive this difference at all. If this is the case, we can define a pixel error threshold, i.e. a perceptual error, difference you can see with your eyes, and consider all pixels within this threshold to be equal. In other words, we're going to average pixel values that have similar numbers. So, the original pixel values in that string are here, but after we average them, they become 1,000, 1,000, 1,000, 1,000, 1,000, 1576, 1628, 1623, 1623. Right, so these are all around 1623, so they average out to that. This is a standalone number, and all of these lower numbers average down to 1,000. So this definitely increases the degree of redundancy, and now we can apply lossy compression to be 6x 156.3y, where y equals 1623 and x equals 1,000. So, lossy compression typically includes two distinct steps: approximating the original data samples with some admissible error to increase data redundancy, and compressing the approximate values with conventional lossless compression. And thus begins the whole lossy versus diagnostic argument. How much averaging can we tolerate without losing diagnostic image quality? Well, compression is not equal across all modalities. This is where lossy becomes more of an art than an actual science. Suffice it to say that the differences between image pixel values can be diagnostic in some cases, such as tiny microcalcifications in mammograms, and purely meaningless in others, such as noise in low-dose X-ray or CT images. Consequently, the same values of compression can be too high for one image and way too low for another. Moreover, pixel value fluctuations can depend on different tissue types, image acquisition protocols, imaging artifacts, and so forth. As a result, there's no universally perfect compression for diagnostically safe lossy compression. And there's no universally perfect RComp value to ensure that your lossy image will stay flawless. This leaves you with only one real option. You have to try it yourself. If you're using lossy compression, you will need to experiment with different compression settings provided in your software to see that the diagnostic integrity of your image remains intact. And you will know when it's wrong. Too much lossy compression will leave you with severe blocking artifacts, or what a lot of people call pixelation. So if you have too much, this nice looking liver here becomes a blocky, ugly mess. And that is all about compression. Oh, one other thing. When you are testing lossy compression, you need to do it with a radiologist. You don't want to test lossy compression on your own. You won't see the image the way the radiologist sees the image. So lossless compression, you can implement that on your own. You can do that by yourself. But whenever you do lossy compression and you're going to put that into practice, you'll want to have a radiologist present and have them check the work of the quality of the images and make sure there's not any checker artifacts or blocking artifacts or pixelation. Thank you for watching.